till now, if you've been coming to this meetup, you learned a lot about all these kinds of type systems that solve all these problems. But all those type systems are for functional languages. And today, I'd like to talk about a type system which can solve a problem that none of the others can. So, what problems does this have?
Is it a linear system?
Yeah, all right. Let's figure this. Okay. This is not good.
You designate someone as a clicker.
Next slide, clicker.
There we go.
Silicon fails, fall back to read.
All right. So what problems do those other types not solve? Hard-coded is often stateful. Just think of the normal file. You can't read from a closed file, but there's nothing stopping you from writing to close the file and then read from it. So that's just the files. They have two states. It's not too bad. But I can do a Google image search for a state diagram, and I'm just going to generate results like this one, and this one with 4 states. And you probably have no idea have little idea what these mean. That's one of the simplest ones. When you have different parts of programming doing mutations, they can interfere with each other. So here's an example where I'm just trying to do this very innocent operation, setting some properties on GUI. And through a series of steps, each which look completely innocent, I have this little mutation slipped in here, and suddenly it overrides the thing that I just tried to do. And it's like I have someone else in my program messing with me. Memory management, just think of your basic malloc and free. If you don't free something after you malloc it, then you get a memory leak. And if you use it after you free it, you have the most informally named bug ever, use after free. What we want is for type to force us to consume that memory exactly once by freeing it, and then forbid us from using it afterwards. One way to solve this problem is what Objective-C does, where it introduces automated reference counting. And that is, every time you have a reference in an object, it tracks it. Once there are 0 references to an object, then it's free. But then if you get cycles in that graph, you get a memory leak. So every time you create one of these references, you have to think really carefully about this messy concept of ownership in order to determine whether you should track that reference. And when I'm doing functional programming, I don't want to pay the cost of doing functional programming. So here's a random snippet from one of my projects. I have this variable labs, I compute it, it's a list, and then I use to compute another list immediately. And I don't want to have to create 2 separate lists just to throw one away. I'd like to know that I can reuse this memory, because it's only used exactly once, and therefore I can't do that. And meanwhile, speaking of functional programming, in Haskell, you can handle state very nicely. A stateful function is something that takes the old state and gives you the new state. So why can't I do that with I/O? I would like people to write putStir, the function to print a string, to be something that takes the old world and gives me the new world where I've printed that string. But the thing that's stopping me is that if I can get a handle on the world, then I can mess around with it and copy it and compare them and throw them away. So because Haskell's type system can't enforce this invariant, that I can only use a world once before I destroy it and get a new world. Instead, I have to do this whole thing with the IO monad, where I write my effects as these IO actions, and I pass them off to someone else, the IO monad, that's going to do all this stuff for me, and I never get to look at the world myself. So what these problems all have in common is that they involve the control of aliasing. And that is, in order to understand mutation, I have to know who all in my program can observe and be affected by my changes. So the fundamental tool we're going to use to solve all these is what this talks about, and those are linear type systems. A linear type is a type that can be used exactly once. And just that is exactly what we want with an algorithm free. If using a reference means freeing it, I want to free things exactly once, and then it's gone, and I can't touch it again. And that's exactly what I want to do with the state of the world. So yeah, if Haskell had linear types, we would not need monads as much. I'm going to spend most of the rest of the talk talking about linear types, but really these are the fundamental building blocks upon which we can build all kinds of tools for dealing with mutation. So once I have this notion of linear type, then I can infer what variables are used linearly, used exactly once, and that lets me figure out where I can use mutation. I can then put these linear types on entire groups of variables called regions and use that to do memory management. I can also put this idea of ownership directly into the type system. I can put an access permission on every variable reference that's going to tell me whether there are other people who can be messing with my variable while I'm using it. And I can trade these access permissions between different parts of the program so that I can know at certain points that I'm the only one who's messing with it. And once I have that level of understanding, over my variable, then I can start to change it and change the type with it. That is, have open and closed files with different types, and have the type that file change so my program runs, and that is type state. But in order to build all this, it's going to take a type stem unlike any you've seen before. And the reason that type stems like the ones that we talked about in previous meetups can't do this sort of thing is that they have this notion of a monotonic truth, that you learn something has a certain type, and then it stays having that certain type. And you can add new information, but you can't change anything. And what I want to do is I'm going to replace this idea of truth with the idea of a proposition as a consumable resource that can be used up and replaced. And so now I'd like to talk about the properties of the system that give us this idea of a monotonic truth. So first, here is the simple rule for typing a variable. What it says is, if in my context I know that x is a certain type, then I can show that x is a certain type. Well, what that lets me do is it lets me write a program like this one that's going to define two variables and then return one of them. I want something that's going to try to type this x and say, what is the type of x? Wait, you're not using y. What's implicitly in this rule is that I can have all this other information which is not used, that I'm just throwing away when I'm typing this one variable. So this property, that in order to prove a proposition, I can... Yeah?
Speaking of aliasing. The text.
Oh. Yes. It does seem to be anti-alias a little bit. You can see the gray border, barely. But
Well, it's linear, obviously, not alias.
all right. So that rule gives these types the property of weakening. That if I want to prove a proposition, I can take my context, just take any piece of knowledge and throw it out, and continue proving with the rest of it. And something I'd like to make very clear is that this is not a rule. This is really a property about all proofs of the system. It says that if I have a proof, if I can prove something from a bunch of hypotheses, then there's also a proof of that same thing from those plus one additional hypothesis. So this little innocent thing is really an entire transformation of like all proofs ever. But really, it all boils down to this one rule that lets me throw things away. The next structure rule is not quite as reductionist. So here we have the rule from lambda application, and this has two parts: the function and the argument. And what this says is that if I'm figuring out the type of this application, then I can take all my information about the type of that thing, and I can use all of it in both parts. And I'm basically copying all my knowledge. And there are all the other rules of simply type lambda calculus or calculus constructions or any of the other nonlinear systems that you've seen before. They all have the same structure, where the thing on the top always has more knowledge than the thing on the bottom. And what this lets me do is say I'm writing this program here, which is going to find a variable and use it twice. I can type this thing and say, what's type this thing? Well, x is an int, x is still an int, and this entire thing type checks. I want something that's going to stop me from using it twice. Then the second time I try to use x by saying, wait, you've already used x, and it is not an int anymore. So this property, and that if I want to prove something, then I can take any proposition any hypothesis I know and just copy and use it twice. That is known as contraction. And the third structural property, it just built so deep into the system that I can't even point to it. Let's look at this gamma, the variable we've been using for context. We've been treating them as sets, where there's a bunch of hypotheses I know. And I can use, and they don't really have any order. I can mix them up freely. But that's not always what we want to do, because what this means is that I can define some variables and use them in any order. And we're not going to get into this today, but there are some very fun things you can do if you disable this and force you to use variables in a certain order. So anyway, that property, that to prove something, you can exchange these in the context freely, is known as exchange. So these are the three structural properties of deductive systems: weakening, contraction, and exchange. And they are together basically determine how our hypotheses behave, and turn them into this idea of a monotonic truth. And what we're going to want to do now, in order to get into linear logic and type systems that can handle a world that changes, is to go into these substructural type systems and these substructural logics, and basically try to drop a couple of those. So before we introduce to the simply typed lambda calculus and its query-Howard correspondence, the intuitionistic propositional calculus. There's a reason we have acronyms. But if we drop the contraction rule and stop us from being able to copy our propositions, then we get into the affine logic and the affine lambda calculus. And in that, you can only use each variable at most once. If I instead keep contraction and drop weakening, where I can't turn propositions away, then that gets me into the strict or the relevant logic in lambda calculus. Quick question. How many of you have heard of strictness analysis? Okay, a couple people. How many of you guys have programmed in Haskell?
Like, technically.
Okay, a few more. Strictness analysis is a thing that makes Haskell not ridiculously slow. And that Haskell is lazy. If you write 2 + 2, it's not.
Which is the contraction rule again?
Sure. So the contraction rule is that one.
Okay.
And it's kind of confusing that normally we read these things bottom up. We say, I want to prove this, so what do I need to know? If you read it the other way, then it's saying, I have this, what can I prove? Then it's like you're taking two things that are the same and squeezing into one. And that's where it gets a name. But really, what it lets us do is copy it.
Right. Contraction is just saying, if I have A twice in my set, well, if you treat gamma as a set, it doesn't
Well, if you
make
treat,
sense to have.
yeah, so once you, basically,
Well, these are exactly the rules that allow you to treat gamma just as a set.
Yes. Basically,
yeah.
without any of these, gamma would be an ordered list. If you have exchanged, then gamma, but not others, then gamma becomes a multi-set. Yeah. Anyway,
So you're saying the strictness analysis allows Haskell to move fast.
yeah. So, check.
Strictness
this-
analysis is trying to understand what needs to be computed and what can be computed right away without waiting for it to be called or something.
Yeah. So normally, if you write an expression in Haskell, every little expression, like both the 2 and the 2 plus 2, the basic semantics say it'll become a func. And what a func is, it's something where when you go to use it, it says, have you already computed? If so, I have that value lying around. If not, then I compute that and put it in there. So, and that's how it's lazy. Because everything comes to computation that's only run when it needs to be, and then it saves a value. The strictness analysis is where file can go and say, okay, that thing is always going to be run, so there's no point in me deferring it into this func. I should be able to just run it now and save a lot of time in memory. And what figuring out that a computation has to be run is basically the same as figuring out that you have a strict type, that it's always used at least once. And so that's exactly what strictness analysis is. It's basically type inference in the strict lambda calculus. So now, if you draw both weakening and contraction, then to give the intersection, you have to use every variable at least once and most once. So you use the exact ones. And then you can drop exchange as well, and you get it ordered. And that's a lot of fun, but we're not going there. So it's already told you linear types, so you can solve all your problems and give you puppies and rainbows. Let's have a close look at it. So this is linear lambda calculus, and I'd like to jump straight into the rules for linear implications. A linear function with type A lolly b, this arrow here is my friend, the lolly. Is a function where the variable is used exactly once, as opposed to your normal function, a arrow b, where the argument can be used as many times as you want. So the way that you create these, it looks identical to your normal functions. You say, if I have a lambda x at m, and I want to figure out what type it is, then I give x a type, and I figure out, using that and everything I know, what type m has. And so if x type A and m has type B, then this lambda is a type A log B. But the way to use it is where it becomes fun. So now instead of saying that I have this knowledge and I'm going to use it in both parts, instead you say, I'm going to split my context into two parts, delta and delta prime. I'm using delta now to show that it's a linear context as opposed to gamma, which is a persistent one. You split it into two parts, and you use one part to type the function, and the other part to type the argument. And that way, you don't have this copying between the parts.
So is it okay to think that delta is just a set of all terms that we have defined up to now, and that we must use them all in the expression that we're typing? So instead of just thinking about abstract context, you just say, in my program, I have, at this point of my program, certain variables are defined. So I must use each one of them exactly once when I'm writing further code.
The second part, yes. The first part about being all variables you defined so far, no. Because right here, so if our context is all variables we defined so far, then each part of this is only to look at some of the variables. So if I define x and y, and okay, well, in the simplest case, m and m are both variables. M is f and n is x. and then I'm going to use my knowledge of the type F to type F. I'm going to use my knowledge of the type X to type X. So up here, when I type this variable, delta is just going to be one thing. It's not going to be any of the other variables I've used so far. And
so it's kind of the smallest set of variables that I need.
it's, yeah, it's
Or
exactly. It's
rather
the exact same
variables
variables
I'm
we
going to
need.
be using. These are the variables I'm
Yeah.
going to be using.
And that's why we call these things in the context, we call them resources. They're they're the things you have to spend to make your program work. And that brings me into variables, which in order to use the variable, in order to type a variable, you need to know the type of variable that was given to it when it was defined. But the other thing is, you also need to not have any resources left about any of your other variables. All those other resources must be used elsewhere. So before, with assembly type dynamic calculus, I was telling you that you could have this entire context with knowledge about all your variables. And now I'm saying, that you can only have knowledge about this one variable left. And that's how we avoid weakening.
So, practically speaking, it means that you can define a variable only when no variable has yet been defined.
No.
No?
So the only binding construct that I've shown you so far is the lambda. And it says that when I define a variable here, I do just add it on like I did before. And now I've actually gained a resource going up because I've gained that variable. But once I start to use it, then I start splitting things apart, breaking it down. And by the time I actually get to the very leaf of the tree, where my entire expression is just one variable, then the only resources I can have at that point that are allocated to that one variable should be the type of that one variable. And fun thing about linear lambda calculus is that your normal products split into two. So here I have what's called the alternative linear product, A ampersand B, or A with B. And they look a lot like normal products in that if I have, a pair A with B, a pair M of type A with B, I can take its first component using all my resources and get something type A, and I can take its second component, get something type B. But the weird thing is, if I want to create one of these pairs, then I can use all my resources and type the first component, and I can also use all my resources and type the second component. These rules are the exact same as the rules for your normal product, but they are different from your normal product. Does anyone know why?
Because you couldn't get both the first and second component of a pair at the same time.
Can you say that louder again?
Well, when you have this element of the product type, you can get the first element and the second one at the same time. Is it right?
Say that when I have the wait, sorry, you could say it one more time.
Well, here you cannot get both of them.
Yes.
You only can get one.
Exactly. I think that's what you said, but I missed some words.
Right. Ordinary products allow you to reuse delta after you have taken the first one and then still get the second one. Now you cannot reuse delta because delta is the same and you have used it up when taking pi 1 and that's it.
Yep, exactly. Once I get the first component of this pair, I've already spent all the resources used to construct this pair. The pair is gone. All that's left is the first component. And so really, this is a lazy pair. That is, if I give you a lazy pair of cookies and cake, that's really saying that I have all the ingredients I need to make cookies, and I have all the ingredients to make cake. But if I made cake, then I can't make cookies anymore. But you get to pick which one at any time. If I do one both at the same time, then I get into the multiplicative products, the tensor products. And for that one, when I create the pair, I do need to split my resources in two in order to create the first and second components. And then when I use it, there's this problem of I need some way to avoid it's just using one part and dropping the other. So I do this funny thing where I can only use it in this destruction bind, where I take both components out at the same time and put them into variables, and then I use the variables in the rest of the program.
These variables must be new, must be fresh.
Yeah, that's basically always implied.
So they could not be in delta, for instance. They must be fresh.
Yeah. Well, that's not very meaningful at this level. It's like so when you're programming normally, you can shadow variables and have them be the same name. But any sane compiler is then going to go and give them different names internally. So these variables are always going to be fresh from the compiler's perspective and from the typeface's perspective. So I can go into the rest of the system if there's extra time, but for now I'm just going to hand away the rest of it, because I think that the parts I've shown so far really get into all the big ideas of how this kind of thing works, and I think the rest is a lot less interesting. The only thing I will say is that we have this bang here, which is like machine. Bang A is like machine that can pump out as many A's as you want, use them or not use them freely. So basically, just because we're using the linear lambda calculus doesn't mean that you can't do all the things you could do before. You just have to mark them as being nonlinear. Alright. So that was this very fundamental type theory. It's just like looks nothing like any program you or I have ever written, unless you were masochistic. But I've already told you about all these real-world problems that this is going to solve. So let's move into some modifications that are going to make that a little closer to something that we can actually use. So first, one thing that's very inconvenient, just using this as a type system, is I'm missing this. So I'm missing a cut rule, and that none of those rules that I had before look like this. Where this rule says, if I can prove something, I can make and stuff in a variable. If I can prove something and type an expression, then I can use that expression to do something else and chain them together. Does anyone have any ideas for how we can do this using the system I just showed you?
To introduce a lambda.
Yeah. So there actually was one rule that did kind of have that form. And then this right here says, it has this form where I'm creating something, and then I get to use it right afterwards in some other part of the program. So I can use that to do this inner trick and create let expressions, where I say let x equals e and m, where I'm creating expression e. I'm creating expression e, stuff in a variable, and then using it later on. That's just creating a lambda and applying it. And when I get to type this thing, then it all checks out. And it does have exactly this form of being able to prove something and then use it. So with assembly type lambda calculus, you can basically look at those rules and then turn them into a program that's going to type check your program. But it's going to be a lot harder to do this with the system I just showed you. Does anyone see what the problem is? So if I were to try to write this as a program, I would say, okay, I have a let expression. Does this let expression type check? Well, let me take my context and use that to type check both all its parts and see if those work out. Except that I'm not doing that here because I'm magically splitting my context into two pieces. And there are 2 to the n ways to use decomposition right here. And I'm just magically saying that I know ahead of time which one is going to make my system type check.
There exists some split that I claim will make it type check.
Yes. You can try out to the end of that if you want. So clearly no practical tool can be built up on using this kind of a rule. So that's why we can rewrite it in a different way. Instead of saying I know ahead of time how I'm going to split this context, I say I have some resources delta I that I have coming in when my type check is let. I'm going to use a bunch of them to type check the E. And what's left I'm going to call delta M. I'm going to use what's left from that, delta M, to type check M. And what's left is delta O. And the resources I have after type checking this entire expression is delta O. And of course, in the middle, I add this resource here because I now have X lying around. And this is really the picture that I want you to have when you think of a linear type checker. That is, I have some resources that need to consume, and I'm just running down my program and using and gaining resources.
It is not going to be finished type checking anything until it comes to the end. Because at the end it might find that some resources are left or something
Yes.
that's not enough.
Well, no system has ever done type checking until it's type checked the entire program. So in order to make this linear,
Yeah, but but it's in C, it's meaningful to say like this line is well typed. It says int x equals 2 semicolon. It's a well typed line. What do you want from me? The line is fine. But in this system, it doesn't make sense to say this subset of this program is well typed because only complete programs can be well typed. And that's what you're saying, right?
yeah,
And it's also true.
Unless you happen to use all your resources sometime in the middle and leave. So that might be the case with the method. But really, that's really what you want.
Some subsets certainly can be well typed, but arbitrary
if I have a
subsets
file
cannot.
that I haven't closed yet, then do you want the type checker to say, oh yeah, I haven't seen you close this file yet, but I think it's fine that I haven't seen you so far. No, you want it to keep going until it's found where you close the file, and if you haven't, it want it to tell you.
If you close the file and read it, then it's already wrong.
Yes.
If you don't close it, then it won't be wrong until the end.
Yep. So at the end of the day, you do want to use all your resources. But if you drop that constraint, and you say you can't have some resources left over, then you're going to wind up with an affine type system where you can use things at most once, but you can have things left over that are unused. And so linear and affine type systems behave basically the same. And that's why a lot of times you'll see people talk about linear types when they really mean affine types. There isn't that much of a difference. So some things like files, you want to be forced to use them, and be forced to close them. Whereas other things such as if you're doing type state, and we don't care whether an account is banned or active when the function terminates, then we don't have to have that restriction. And so
you don't care if you free all the memory over the course of your entire program because the OS will take care of it for you, but you might care if you free a known amount of memory in every frame, for example, because that's what a memory leak looks like, right? Whereas if you leak memory when main exits, that's fine, no problem. Operating system takes care of that shit for me. So like it's like in some cases, like it feels like for any resources, almost any resource, in some cases you're going to be like, yeah, affine is fine, and in other cases you're going to be, I need to be linear, depending, like, and sometimes it's going to be the program at large needs to be one way, and parts can be others, and the other way around. It seems like.
Yeah, and really there's a design decision to be made with correctness. So like, no, if you have a nice batch program, it's like reads in a file and it does some stuff with it, you probably aren't going to encounter any problems if you have that file left open at the end of it, because you can trust the operating system to clean up for you. But a lot of programmers, myself included, will still tell you you should close the file. It's a bug, and there are reasons such as, well, if you might change this program or copy paste it someplace else where it does need that file later, or where it's longer running. Like if I want to make this part of the server instead of just a command line tool, and so we do have the option of having our type system enforce the constraints that you must close your file and free your memory, even if it won't actually cause any user problems in the current version of the program. And the exact same way that the type things we've seen before can force you to do all kinds of things, even if there's a way to not do that and still have a working program.
Do you lose anything if you go into this into the second way of type checking by saying you start with something and you end up with something?
Yes. So first, I've handed this bit left an important part out, which is when you go into this first part, you don't always know what resources you're going to consume. You know, like you might have two parts of an if branch that use different resources. Or also, like the lazy pairs I've shown you, you have to use the exact same resources in both parts of the pair. If you use 2 cups of flour in the cake, you also have to use 2 cups of flour in the cookies. And you don't always want that, so you have other systems where you don't have this property. And so you're going to need to do more complicated things in order to track your resources. And this is called resource management, and it can become a very hard problem. And then the other thing is that it's kind of sort of implicitly written into here that the first part of this expression, E, gets first dibs on all the resources. And recurring type checks, that usually won't be a problem. But you can imagine systems where it actually does make a difference. And also, it definitely makes a difference on where you're going to see an error message. Oh yeah. All right, shall we move on? Okay. Yeah. So one other thing that this format lets us do is it lets us base. Once we use a variable at one type, we can then get a new resource that lets us use it at a different type. And so the types of our variables can change. And so really, it says on the tin that the linear types are types that can be used exactly once. But the big thing that what this lets us do, and the reason we like them, is on top of that, we can create flow-sensitive types. That is, types that differ depending on how you got the current place of the program. And that is the key ingredient in understanding a lot of imperative code. And it's with that in mind that I'd like to show you a bit of an actual tool that uses linear types at the core to help reason about Java programs. So this is the checker framework. It extends the Java types in all kinds of ways to catch all kinds of problems, such as right here. Okay. Format strings, immutability, hinting, and whatnot. Yeah. And it takes advantage of the fact that in the new Java, there's a syntax change where you can put a qualifier in any type, and to use that to let you extend the type system. And this is a very practical tool. I use it at work. So a lot of these things look like they should have nothing to do with linearity. like units. But because we're dealing in the presence of mutation, then at the core of this, there needs to be linear types to help to obtain that. And so I'd like to dive a bit deeper into the nullness checker. So what you need to do to have a types in for nullness. So here I have a simple program. It's basically a function that takes the first name and the last name and gives you a full name, except for some reason I've like parameterized out the space and stuff in the class because that's the kind of thing Java programmers like to do apparently. So I've said that last name can be null because, you know, like there's a professor Arvind at MIT who only has a first name, so you've got to support him. Maybe he's grading this thing. So it first looks like the only types you need are to add on non-null and nullable annotations. You know, say the first name can't be null, but the last name can. But this is really a lie. Name delimiter is not always not null. You see why?
When the last name is null, you don't need delimiter at all.
What?
Like when the last name is null, you don't need name delimiter at all in this code.
What was that?
He's saying that when last name is null, right? Then the name delimiter is not used.
Yes, that is true.
So then this function is not called, and then it's not assigned. It remains null until it's not assigned.
Exactly. So right here, name delimiter is not null because it's not initialized yet. And so you can never just have these straight up non-nulls when you have mutation and initialization around. And that's why you need linear types. And so we also need to put on initialization qualifiers that are going to tell us these things are initialized. And also that the implicit this reference is initialized. Because, you know, like I could call this function from in the constructor early on and have it break your program, even if I say things are non-null. And don't worry, using checkers doesn't actually look like this because
So
yeah?
So if the field is annotated with initialized non-null, that means that it is non-null when the whole object has been initialized. It doesn't mean that it's always.
Yeah, what does,
Yeah.
what's
It
going
means
on?
it means when the object's initialized, and so is this thing.
It still is not true.
Hmm?
It is still not true because the object is initialized, but.
And by initialized, I mean when the constructor completes.
Oh, okay, good. Okay.
Which is kind of what initialize means, yeah.
Yeah.
Oh, I didn't see the name actually. It's too small for me.
Yeah.
Sorry.
I didn't see that this was a constructor.
I trust there's a application of this initialize thing that actually solves a problem that would exist. Whereas like in this, the obvious thing to do is initialize it in the declaration.
Yeah, so
I mean, 20 examples
main,
are 20 examples, so
yeah.
yeah.
The main purpose of this initialize thing is really just a helper to help us deal with the knowables. The actual problem that it would solve would be mainly calling methods from too early in the constructor. That's it again.
So who is writing the program?
Yeah, that was what I was just getting to. These are virtually all inferred, which makes this thing usable. Yeah, so all the initialization things are inferred. And non-null is put default in everything. So the only thing that you write are the knowables. And in practice, it turns out I think I write about one knowable annotation for every 60 lines of code. So, so I converted our entire Android code base to use the nullness checker in about a day. fun doesn't stop there with these initializations. Because it's a bit oversimplistic to say that when I start a function, a variable is either maybe null or non-null. Sometimes I do need to know that some more variables are non-null that I might in other places. So I can also put on these requires non-null and ensures non-null annotations. So here I have a silly little class going to use this one, and it has its own internal name utils. And I'm building with a type system that I need to initialize name utils before I call this print attendee list. And so I want something where if I initialize name utils and then use it in this, that will type check. But if I flip the order of these two, then it won't type check. And so these annotations here are basically a very simplified form of type state, which I mentioned earlier.
So is it fair to say that the type checker introduces some invisible variables that have linear types, and then introduces some invisible code in the linear lambda calculus, which is then type checked?
No. There might be a way to formulate it as that, which wouldn't mean much. As you'll see in a moment, it's more accurate to say that I have both a linear and a persistent type attached to these variables. This string, that is a persistent type. It's going to stay a string. But this initialized is a linear type. So the amount of machinery that you need to go from to get from the system I showed you earlier to something that's going to actually power this is quite a lot. Like you look in an actual paper that's using type theory to solve a software engineering problem. All the type rules are like whoop, because they have to track so much stuff. But the fundamental principles behind it are that you have some persistent knowledge and some linear knowledge. So rather than saying more about that, I think let's just jump into showing you how this thing is actually type checked. So let's start with the constructor. So I start off with my context. In there I have initialization annotations on this reference and on named limiter. And named limiter is uninitialized, and this reference is currently being initialized, and so far the empty set has been initialized. But this space here is an initialized string. So when I do that assignment, then this uninitialized qualifier dies, and I replace it with a new initialized qualifier. And this thing dies, and I now know that it has type under initialization where a named limiter hasn't been initialized. Since this class only has one field, that's the same as being initialized. And so I know that this class has been initialized after the constructor completes, and so this constructor type checks. Meanwhile, when I go into the full name function, at the start, I just know that last name is nullable. But when I go into this else branch, the type system can see that this is checking last name for null. And so it knows in this else branch that it can throw out that non-nullable type, that it can throw out that nullable annotation and replace it with a non-null annotation. So it knows in this line of code, last name has to be non-null. And that's why it knows I can do this concatenation without it blowing up. And so that function type checks. So now I have these magic ensures non-null and requires non-null methods. That's going to tell me this very strong property about my control flow and what happens after this function. But really, that's pretty simple to type check. So what it says, at the start of it, I know that name utils is nullable, but I have this argument for a different nameutils object, which I know is non-null. I tried to put this here explicitly, but everything's default non-null. So when I do this assignment, I know that this nameutils object is non-null. And so I finish the function, and I see that nameutils is non-null, and so this invariant is satisfied. And now when I go to use this, I start off just by knowing that the nameutils in this attendee list is nullable. But after I run this in nameutils, then this annotation here is going to tell me that I can now treat that object as non-null. And so now that I know it's non-null, it will satisfy this contract. And so this thing is going to type check. Whereas if I swap the order of these, it would not type check.
You have to give it the ensure is not nullable hint.
In this case, yes. Because otherwise, because this thing here, the way it's currently written, if nameutils is null, I'm including a null pointer exception right here. And the guarantee of the nullness checker is that unless you suppress it, which you can do, if the nullness checker passes your program, then you're guaranteed to not get any null pointer exceptions. And so we can't have that. So you have two choices. You can either rewrite your program a little bit, which I'd recommend because there's probably no reason for this not being in the constructor because this is a dumb example. Or you can put this annotation saying, I need the programmers to have done something to ensure that this thing is non-null before I get here. And then
couldn't the checker infer that the ensure is not null?
Yeah, it feels like both of those annotations should be inferable.
They definitely could be. But there are a couple problems with that. So the first is just a matter of efficiency. Now you're getting into a whole program analysis. Like right now, every func method can be type checked, and the only thing I need to know about any other method is the signature. Now you're wanting me to have already done this analysis of every method first. Well, first, I don't even always have the source code. But even still, what you're wanting to do is like track what every function does to every variable and get this and do this in some order and do this crazy thing. And that's full program analysis. Like this thing, this type checker is pretty fast, but it still does speed up my compilation times by a fair bit. It would be way slower if I wanted me to do. But there's another problem with whole program analysis, which is basically now you're telling me that I can make this little bitty bitty change in one part of my program, and I'm going to get a type error way off somewhere else. And that's a big thing that I don't want. And it's not just a matter of the type checker, that's actually saying, like, if I don't enforce these contracts locally, it's going to make the entire thing work, then I can make a change in one place and have it that causes it to crash way off somewhere else.
Okay, I'm not following that answer because we all can see, you know, if we just look at that init nameutils with our human brains, it's quite obvious that at the end of that, this dot nameutils is null if and only if the argument to init nameutils was null. And since you said that non-nullable is the implicit binding for all parameters, therefore,
and
so like that annotation that is on init nameutils seems kind of obvious, and I didn't have to look at the rest of the program to know that at the end of init nameutils, this dot nameutils wasn't null.
Yeah, and that's exactly true. But the big question is... And
similarly, I can look at print attendee list and see that, and this one's a little more subtle, but I can see that as long as attendees is not an empty set, that nameutils dot is a substring of the code, and therefore nameutils had better not be null.
Yes.
And again, no whole program analysis. So like,
So you certainly can infer these, as I told you. And since this program isn't very large, program analysis is not at all.
but again, it's not whole program analysis, right?
Well, it
It's-
is because you have to
What if there
know-
was like a
Yeah.
branch and you're
So,
initialized
okay,
and it
so
called something
I'm
somewhere else?
jumping straight to whole program analysis. So really, I should use more precise terminology in interprocedural versus interprocedural analysis, and yeah, and right now I've defined the system. Well, okay, not defined. From what I've told you so far, you can type check every method individually, and you might not have to jump up to the whole program level, but to do what you want to do, I do still need to incorporate knowledge from having type checked other methods.
That's exactly what I'm claiming is
Yes.
not the case.
Okay.
I might be wrong. But
Wouldn't we have to
anyway,
figure out if attendees can be empty or not? Because if attendees can be empty, then we don't necessarily know that it requires non null.
Yeah. So.
right. If we
Yes.
cannot guarantee whether attendees is empty or not,
That cannot be.
then it must not be null. If we
we cannot find this. This is computationally infeasible to find out whether it will be ever empty or not.
But either way,
yeah, and
putting aside the slightly more, I agree that the print attendee list is a slightly more complicated case, but certainly no inter-procedure analysis is required to notice that at the end of init name utils, this dot name utils has been ensured non-null.
Oh.
So it seems like totally inferable.
Okay. So,
Anyway,
so
like, I mean, maybe the tool, maybe it is inferable. Maybe there's a small patch available to checker that would solve this problem, and it's just not in the tool or not. I don't know. But
all right. So I think this is a very important question, so I'm gonna stick with it for a bit longer. So yeah. So what you're getting at is that basically. So. Okay. Yeah. I guess. Okay. So yeah.
Well, the first question is, do we ever call this init name utils? Unless we know this, we won't be able to say very much about whether it's initialized or not.
what?
Yeah. Well.
No. The types of that's not what types are, right? Like it doesn't matter whether we call it or not. If we never call it, but it's ill-typed, then it's ill-typed. And if we never call it, it's right? Like it doesn't matter whether we call it or not. It's not a dynamic check. It's a static check. And it's and again, right? Like there is exactly one code path through that. You can call it a method or a procedure or function,
All right.
whatever feels good at the moment. But like, there's exactly one code path through that procedure, and that code path invariably has the effect of ensuring that this .nameutils is not null,
Yes.
because of the precondition that the parameter is also not null, which you said was implicit unless declared otherwise.
Yeah. I should have written it down.
So I'm assuming that that's there, invisibly in 0 characters, that there's a non-nullable there. And given that that non-invisible non-nullable is present, like, anyway.
Is there an example that shows that what he's saying isn't true? Like, is there one?
No. So what he's saying is exactly true.
Okay.
Although I think he's misunderstanding what it means to be interprocedural. But I'm so much to explain a bit more why a lot of the times you actually don't want that. So right now when we're type checking this, if I didn't already have the annotations lying around, I would have to go in here and infer them. And so in this case, everything I care about with this type is just this simple set of nullable annotations, and it's a very simple summary of what this method does with regard to nullness. That's still an interprocedural analysis, and so there's a little bit of a problem with determining what order to run these analysis, especially if you have cyclic recursion. In this case, I don't think there's probably a pretty easy way to handle cyclic recursion. It's not that much of a problem, but it still is an interprocedural analysis. And it's, but my claim is still that you would not want to do that, at least not in this case. At least not in most programs. You do not want to do that even though you could. And the reason is basically, suppose I didn't write this annotation here, then is it or is it not a part of the contract of this method, this happens to make this thing non-null.
That's a special case of the general rule that that written, like types that consume bytes in your program are written first for other programmers and second for the compiler. That's
Yeah.
all right.
Okay, so actually there is a problem in that Java is an open system with late linking, and so if I then have a subclass, well, first, in order to infer this annotation on the superclass, I need to go look at every subclass, and I don't always have every subclass available because some of them can't be loaded late in the game. But also,
yeah. Whereas when you write the annotation, you can propagate it down through the classes at the time that you link them, and say if you didn't meet the annotation, then you are not a subclass of this. So
exactly.
I don't know which of these lines is wrong, but it's one of them. It could be the one where you say you're inheriting. It could be the one where you implement the function wrong. I don't know.
Exactly.
Yeah. Okay.
Like in the same way that you can't override them in Java, you have to declare every exception that you can throw, and you can't override a method with something that can throw more exceptions. And I smile every time that happens because it means you can ask me questions.
I don't feel that exception checking is a good argument because there's unchecked exceptions, which are a huge deal. But anyway.
Yeah, I paved over the runtime exceptions. But as far as things that extend exception in Java, like you can try it right now. To make a class and then make a subclass, override a method, put a throws blah 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 clause, and Java will complain. Yeah. So in addition to the subclass problem, which it stops us from doing a lot of things in Java. There's also just the problem that's, do you want it to be part of the contract that is going to make this thing non-null? If you put that in this annotation, then you're saying anytime I change this program so that it doesn't do that anymore, then it doesn't type check. Whereas before,
even if I happen to have, before doing that, deleted all the other functions that depend on it.
Well, if you do that, then you just remove the annotation too.
Yeah, exactly. No, I mean exactly. Like if on your next slide, the first step is you delete the second line on your next slide, and then you come back and you screw up init name utils. Like, if it's part of the contract and you screw up init name utils, it's still a bug, even though the bug never gets triggered because you deleted the print attendee list line.
Yeah, so the way I've written it now with this annotation, if I delete this line, I get a type error here. Whereas if I delete this annotation and then I do this line, I get a type error here. And that's confusing. So that's the reason that you often don't want to do a whole program analysis, even if you can. Does that answer your question?
Well, my question was just, is it possible or not?
Oh, yeah, it's definitely possible. So, all right. So that is the fundamental principle of how the Loomis checker and checker framework works. And this is a totally practical system. You can use it on your favorite Java program. I do. And even though we just have this very classical thing, which just controls what values a variable can have, because we mixed in all this mutation in Java, then we've had to add in linear types. So you now know what all these symbols mean. This is how we talk. So whereas before we'd been living in this pure functional world, where types were types and variables had one type, we've now consumed that and gone into a new world where we have linearity and we can deal with change. and linear type is the fundamental building block upon which all this stuff is built. It's part of every practicing type theory standard toolbox. Like, I've seen papers that don't even mention the word linear, and yet still clearly are building this kind of type stem with deltas and adding and consuming resources. And all this stuff put together, we've seen how it's useful just to help remove this very large and pervasive class of bug in Java. And because of the power and how much flexibility it gives us, we can solve all these other problems with mutations too. So I won't talk about a fraction of the problems I told you can solve, but this is a huge field. It's used all over the place because apparently imperative languages are popular or something. So there's a bunch of other stuff you can read about it and see how to deal with those other things. Right.